All right, what's up, everyone? Um, if you clicked on this video, then you're probably here for two reasons. The first reason is that you want to see what my template looks like, or the second reason is you want to get advice on how to write your own template and what's important to keep in a template or not. Now, I don't really need to go into why templates are helpful. They're like, it's essentially just a place where you can put a bunch of like pre-written code so that in official like Codeforces contests or like CP contests in general, you can just like take that snippet and just copy it into your current solution, and you don't have to spend any time like rewriting code that you already know how to write, but it might be slightly long, and that's just going to take up time. So I think I'm going to go first into what my template looks like, and along the way, I'll just kind of explain what parts inside my template are probably helpful and what parts probably aren't really necessary to include in your own template. So yeah, without further ado, let's just get right into it. Okay, so as you can see, this is what my template looks like. Um, just a disclaimer, you could probably tell by a thumbnail, I use Java, and that's the only language that I use in CP, and I actually don't know C++ well enough to comfortably use it in programming contests. So my template is entirely Java, but the good thing is that Java and C++ are similar enough to where you could probably like still learn a lot from my template if you're a C++ user. So yeah, without further ado, let's just get right into it. So if you're Java, if you're like a Java main, then you know what these statements mean. They're just like import statements. Utility like for array lists and like whatnot. IO is for like input output. Math is just for math. I don't know, like whatever. And okay, this is actually a really interesting trick to point out. These three import statements at the top, what this allows me to do is that if I wanted to take the minimum of two numbers, instead of writing math.min of like a and b every single time I want to take a min, if I have these import statements at the top of my code, I can just write min of a and b. And I know that doesn't sound like a really big deal at first, but sometimes because min and max are like such like common like functions you would use, if you have like math.min, math.max, like just in like a bunch of times, it can like clutter your code a lot and it makes it a little bit harder to read. So I think if you use Java and you don't know about this, I think this is actually really cool. And right above these statements, I just have like my comments. This is not really important. I just kind of put things that I want to put. So I guess I'll just go into really quickly what this means. Butter is a BTS song because my favorite K-pop group is BTS. So Stream Butter, it's a good song. I like it. These are just like some random Twitch emotes from, yeah, there's like Twitch emotes from Tectone. If you know what Tectone is, then good. If you don't, then go follow him on Twitch. He's a cool guy. I Need You is one of my favorite BTS songs of all time. And it's actually a song where I'm currently learning how to like dance to it. I don't know. Like, I just like the song. And Shower Run is a Genshin Impact thing. Why did I spend like 2 minutes talking about what my comments at the top meant? I don't know, but we'll just move right along. You're probably not very interested in that anyway. So, in my main method, I basically just have some standard like input output, because the thing is that in Codeforces at least, there's a lot of problems where the input format is like you have t as like a number of test cases, and then like for every test case you have like an integer n, and then integer n you have like to read an array of n integers and like so on. So I just have like that template copied over here, just so like if a problem has that input format, I can just like say I can literally just spend no time like actually implementing the input. And to be honest, this isn't very helpful. I mean, it does save time, but it only saves like a minute at most. And in a minute, it doesn't really make that much of a difference in the performance of a contest. Yeah, but that's whatever. This is just a helper function that helps me read an array. So like in case if a problem requires you to read multiple arrays, then it's just really easy to do that by just calling this method. This is just for debugging purposes. So pretty much when I'm debugging and I need to print what the contents of an array are, I just have this method here just so I can just say print this array, and then it'll print all the elements on one line. And it just makes debugging a little bit easier. And again, it's such a short like line of code that it doesn't really matter. Okay, so I have a bunch of comments over here, and I think this is actually kind of interesting. Basically, like as I solve problems or as I upsolve problems, whenever I come across like a problem where like, for example, if my solution was wrong or like if it was returning like TLE or runtime error for some reason, and every time like I come across like some error that happens, I like write it down in here. And what's really nice about this is that when I'm stuck on a problem officially and I have like no idea what to think about, sometimes I'll actually refer to what my notes are in here and like realize that, oh wait, this problem can actually be reduced to like this observation that I made about a different problem that I upsolved like a month ago. And it's just like really helpful. I'll just very briefly like show like one or two of these examples. So for example, okay, don't worry about this. This is just kind of a meme. Um, I guess what's a really good one? Um, I think this one's like a pretty niche one. That's also like kind of cool. So like basically, I upsolve a lot of problems to where the problem itself doesn't initially look like a graph problem, but the problem has like a property that requires like pairs of elements, or like you have an association between like one integer and another integer. And often you can turn those into a graph problem, and that makes the problem easier to visualize. So this is like kind of one like tip that I have in here, and this has actually helped me solve a few problems, or like at least help me like get some problems much faster than if I didn't like think of a problem as a graph like immediately. And the nice thing about this is that even though like you won't necessarily like I won't necessarily read like all of these notes every single time I try to solve a problem, having these notes here makes it easier for me to like kind of remember what tricks I've done before, and it's much harder for me to make the same mistake twice. So I think that's what's really like powerful about this. And if I had to be completely honest, this might be the most useful thing in my template, which is kind of interesting because it's not even real code. But yeah, I feel like not many people actually do this, and I think it's really useful to do just for like your own practice sake. So, I mean, if you don't want to do it, then that's fine, but that's just what I do. None of these methods are super interesting. It's just like read an array of longs. Not super interesting. This is to check if a number is prime or not in square root n. It's not very interesting. GCD, Euclidean GCD, pretty standard. This is a totient function, and I actually have two implementations. One is a square root of n totient like function calculator, and the second version over here in the comments finds all like 5 values from 1 to n and n times ln of n. I actually don't really use this method. I think I've used it like 3 times ever, but it is nice to have in case if I do need it. This generates a array list of all the divisors of n and square root of n time. Pretty standard. Okay, this will only be relevant for people who use Java, but I think it's pretty important to point out. So if you have like an array of integers, arrays.sort uses quicksort. And the problem with that is that even though most of the time it's n log n, if in some cases, for example, if the array is already sorted or if the array is in reverse order, quicksort will degenerate to O of n squared. And that's really bad because in problems like Codeforces, like it's pretty common for a single test case to have like an array that's like already sorted, and then arrays.sort, instead of running an n log n, it would run an n squared time. And that can really like screw up your code, and it's really easy to get hacked and stuff like that. So that's why I wrote my own sort array. Basically all I'm doing is that I'm taking all these numbers, putting it into an array list, and I'm sorting the array list. And the reason why this works is that collections.sort uses merge sort, which is always n log n no matter what. It doesn't degenerate to n squared like quicksort does. I guess I should write that down. Collections.sort uses merge sort. So yeah, this is the reason why I have this method, and I think this is actually kind of helpful. This is just fast exponentiation. I think this is a pretty standard method. I don't really need to go into it. This is a custom multiset. If you use C++, this isn't really something you have to worry about because C++ already has a multiset implementation. But if you use Java and you want to like kind of use a multiset, then you can actually use a tree map where the map where the key maps to the number of occurrences of that key. And so having these two methods is just kind of like a helper function for me. It just makes it easier to like implement a multiset and like remove and add elements into it. This method, it basically coordinate compresses all the values in array at I. So for example, if you have a problem in which the contents in array at I go from 1 to 10 to the 9, but you only care about whether a number is like strictly greater than like another number like in relationship to it, you can compress these values to like 1 to n, and it would just make implementation just a little bit easier later in the solution. Power and multiply, these are used for matrix exponentiation. I don't really use these very often. I think I've only used them in Codeforces like once when I was upsolving, but aside from that, yeah, it's pretty standard. It's not much else to say. It's pretty much just like the multiply function just multiplies two matrices together, and the power function is just a slightly modified version of the fast power function up here. Let's see. Okay, so those are pretty much all of my like smaller methods, and from here on out, it's just a lot of most of them are going to be data structures. So the first one is the disjoint set union, also known as union find. This is what my implementation looks like. And the way I have it set up, it makes it really easy to not only have like the actual DSU itself, but it's also easy to keep track of the size of each component within the DSU. And you can also adjust this to do like other things. Like for example, you can check like bipartiteness of connected components as well and stuff like that. I have the find and the merge method. And something interesting to note is that my find method only uses path compression. It doesn't actually use find by rank. And I know that using path compression plus find by rank makes it like n times like a really small factor, which makes it essentially O of n. But without find by rank, this could go up to log n. But like in the end, like when you're using union find, it's like there's not that much of it. N log n is still like an acceptable runtime. And I believe even then, like path compression makes like that log n factor like have a good constant factor anyway. So this is like sufficient in terms of like Codeforces and like CP in general. But yeah, that's my DSU template. This is my Fenwick tree template. The interesting thing is that I feel like not many people refer to the binary index tree as a Fenwick tree. So like I guess this is just a binary index tree. Yeah, it's pretty standard. I won't go too much into it. It's just like a really fast way to have online sum queries. Okay, this is actually really cool. This is an iterative segment tree implementation. Now, this is not mine. This is actually, I believe it's Talato Ani's. So this Talato Ani's is handled on Codeforces. Talato Ani's segment tree. So he's like kind of good. Kind of good is an understatement. He's IGM on Codeforces. So if you want to like check out the stuff that he does, then like friend him on Codeforces or something. But yeah, basically, I ripped this implementation of a segment tree from him because it's iterative, and in general, iterative like implementations of data structures have a better constant factor than recursive solutions, even though recursive solutions are a lot of times much easier to implement. As you can see, like the iterative segment tree just has like a bunch of like bit manipulation like this, and it's just like, why would you ever do this efficiently, you know? If you're going to use an iterative segment tree, you might as well just have a template for it. So yeah, that's the segment tree. This is a lazy segment tree. This is my own implementation of a lazy segment tree, so it is original. And this one is actually recursive. So because writing an iterative lazy segment tree would just be really annoying. I'm not going to go into it too much because I don't want to. But yeah, what's nice about this is that it's pretty concise and it's easy to understand. So if I need to adjust this segment tree to like do different things, so for example, right now I have it as like updating as like an increment on a range, but it's not too hard if I need to change it to like set a range to a certain value or stuff like that. So that's what's nice about this lazy segment tree template. Range bit. This is essentially just a Fenwick tree that can update on a range. It's actually pretty interesting because it's a constant, because it has a much better constant factor than lazy segment trees. And what's also nice is that it's an iterative implementation. So if you need a lazy sum segment tree, but you're like TLing because of like constant factor, then you can use a range bit instead, and that will help out a lot. And I think I actually I remember using this pretty recently to get to upsolve a 1C, and it was like really fast. Like they gave a 3-second time limit for the problem, and my code ended up running in less than 500 milliseconds using a range bit. So that's really nice. Sparse table, just like O of 1 min queries with n log n pre-comp. It's pretty standard. I won't go too much into it. This is an LCA template. Basically what I do in here is I input a tree and the root of a tree, and then I basically have helper functions that allow me to query the LCA of 2 nodes. The thing is that I actually don't really use this template anymore because I understand LCA well enough to where often it's easier to just implement it from scratch. Because if you're already doing the recursive DFS, then pretty much all you're doing is that you're just populating the first DP layer with the parents of each node, and then you just use binary lifting step, which is like 2 lines. Like it's really just 2 for loops or 3 for loops. Like 2 loops, like 3 lines in total. So yeah, bitset. I rarely use this ever, but when I have used it, it has been super helpful. Because basically, I remember the last time that I used bitset in my template was when in, I believe, ICPC regionals in the fall, and we were able to solve, and I was able to solve this problem using this template, and that was enough to like essentially speed up an n, like I think it was like 4 times n cubed to 4 times n cubed over 64, where n was like 1500 or something like that, and that was just enough to like get that problem from TLE to accepted, and that ended up being one of the harder problems of the contest. So that was really nice, and that was like one time which bitset was like really helped me out, but I don't think I've ever used it in Codeforces before. I'm just be honest. But aside from that, this is pretty cool. Okay, and the last thing is a MaxFlow template. Now, what's really interesting about this is that I actually implemented this from scratch. Like when I learned MaxFlow, I made it a goal for me to like actually understand how DNIT work, so that I could just implement this by myself and just have a template that I could claim as my own. It's kind of long. I mean, it's MaxFlow. Since when is a MaxFlow template not long? But yeah, this is pretty much, it's honestly pretty standard. Like if you know how MaxFlow works, pretty much just you add edges and and then you just do BFS and DFS, like to find the dual graph, like whatever. Like I'm not going to go into the details too much. If you want to know MaxFlow, then there's actually like some really good like video editorials on YouTube already. So just like look it up and you'll probably find them. Yeah, and the last thing in my template is a fast scanner. Now, this is only relevant if you use Java because C++, the normal way to read input is already very fast. But in fast, basically what this does is that sometimes buffered reader and string tokenizer, at times that is not like the fastest way to read an input. So when there's a ton of input in a problem, and to where a point where reading an input could be like a contributor to like TLE in that solution, I'll use fast scanner instead. And the fast scanner is extremely long. It's like over 100 lines, but basically this is like, I'd say it's probably like 20% faster than using like buffered reader and string tokenizer. So that's pretty cool. And yeah, that's pretty much what my entire template looks like. Now to go over like kind of what are some important things that you could include in your template, or what things that you could adopt to your template. Just like these small methods over here, like stuff like maybe like finding divisors of a number n, or like fast power, like fast exponentiation, or stuff like compressing an array. I think these are things that you could include in your template, and that would be kind of useful because even though the methods themselves aren't very long, what's more important is that you know that this code is already correct. So not only can you just copy this like method over into your existing solution and work from it, but if you're debugging that solution, you know for a fact that the bug cannot be in this method. And the only time that the bug can ever be in your method is if your template was flawed in the first place, which actually happened to be pretty recently in Deltic's round, where there was like a small bug that I had in my push and pull method that I didn't account for because I was just being very stupid. But yeah, just make sure that if you're to include something into your template, make sure it's absolutely 100% correct before putting it in there. That way, if you ever use it in the future, you won't ever have to worry about finding a bug in it. So, and honestly, I think that's the power of having templates. Not necessarily saving time, but rather just making debugging easier. Because even if you were to write like, say, like matrix exponentiation from scratch, if you know how it works, it probably wouldn't take that much time, maybe like 3 minutes of just coding to like actually implement it. But if you were to debug the problem, it's possible that if you're writing matrix expo from scratch, you would make a bug. And it would take like, who knows how long time it would take for you to find that bug. But if you already have like a matrix expo template that you know for sure that's correct, and if you find a bug in your code, you can eliminate the possibility that the bug is within the template code. So I think that's where the true like power of templates come in, where it's not like, sure, they save a little bit of time, but they save a lot of debugging time if it comes down to that. I think these data structures are pretty good to have, just like Fenwick tree, like DSU, segment tree for sure, because, you know, a lot of problems use segment tree nowadays. So if you can just like copy paste segment tree template code, you could probably like save a good amount of time. What I will say is that I think it's important to understand most of your template code. So what I mean by that is that you can have like a template for like a really complicated data structure, and even if you don't understand how it works at first, that's okay. Like if you don't understand how segment tree works, but if you know how to use a segment tree in the sense that you know when to reduce a problem to finding like a range max query, then you can have a segment tree like implementation in your template and just copy it over from someone else. And even if you don't know how it works at first, I think that's completely fine. But I think it's also important in where like if you want to like improve in the long run, you should eventually know how all of your data structures work. And eventually that boils down to being able to implement everything in a template on your own, or like at least most of it. So like, I mean, in this example over here, this segment tree code is not mine, but the reason why I still have this over here is because I have a lazy segment tree code over here, which is mine. So obviously, I understand well enough how lazy segment trees work, and if I understand how lazy segment trees work well enough to where I can implement one from scratch, I can also implement a regular seg tree from scratch. So if I were to have like a separate template like this, I might as well just have the best possible implementation of it, if that makes any sense. Just have like these data structures. I think these are helpful to have in your template. LCA, I don't really use this, like I mentioned earlier. But yeah, I think what this boils down to is just when you're solving problems, think about what like method or what like algorithm you're using like frequently. And if it appears frequently enough to where you could like just write a method for it beforehand and just copy it over whenever you need it, then I think that's a good time to add it to your template. I don't think it's a good idea at all to like take some LGM's template and just like blatantly copy the entire thing and just claim that as your own template. And because I think a problem with that is that one, it's code that you haven't like written at all on your own, so you won't really understand how exactly it works. And two, like even though you don't have to understand like everything that happens in your template, that doesn't mean you shouldn't understand anything that happens in your template either. So like It's okay if there's like one or two things in your template that you don't completely understand how they work, but that doesn't mean you should like not know anything in your template, if that makes any sense. You should at least know like a good amount of your template well enough to where you can just write it from scratch. And the only thing you would save is like maybe a few minutes of time. But yeah, this is my video on my competitive programming template. Woo. I hope you found this informative, or if it's not informative, I hope this was at least entertaining for you. I'll put a link to my code in the description below. And yeah, if you enjoyed the video, then thanks for watching, and you should subscribe because we just hit 1,000 subscribers. Right, I forgot to thank everybody for 1,000 subscribers. Oh my god. Yeah, like that was so crazy. Like, thank you guys so much for subscribing and watching my videos. I really didn't think that I would get so many views or like subscribers in the first place in literally just over a month. So that's absolutely insane. Yeah, if you have any suggestions, then just leave them down in the comments and I'll try my best to get to them. See you next time.